So let's start off with a little joke. So here are two flasks talking to each other. Seriously, dude, I think you're overreacting. I know, I love that. I think it's funny. All right, so you don't need to overreact. We're going to be working on calorimetry today. And calorimetry is pretty straightforward, and it's going to take advantage of what we've already learned about calculating delta H. So we know that energy cannot be created or destroyed. That's what we call the first law of thermodynamics. It's also referred to as the law of conservation of energy. So that's pretty common knowledge. So energy is transferred. So when you have a system, we've already talked about this some, you have energy is transferred from a system to surroundings or from the surroundings to the system. So how do we use that in calorimetry? Well, we're going to take advantage of this energy change in the surroundings to figure out the energy change in the system, because we know that the energy lost by the system must be gained by the surroundings, equal but opposite sign, or vice versa. Or if the energy is gained by the surroundings, it's lost by the system. Did I just say that? So that the law of conservation of energy applies to the system and the surroundings. All right, so if we know the delta H of the surroundings, we know that the delta H of the system is the opposite sign. Same numerical value. And then we can substitute in our equation m times c times delta t for the surroundings and m times c times delta t for the system. Again, we have that negative sign on one side because the energy is flowing in one direction. So energy gained from one is lost from the other. So the negative sign is important. Okay, so we're going to see how this applies in some problems. Oh, right, there's that whole concept of thermal equilibrium. So thermal equilibrium is really important here because the two objects at different temperatures, when they're placed together, will come to get to the same temperature. That's just a fancy way of saying they flow, heat flows until they're at the same temperature. So what that means is the final temperature for both the system and the surroundings is the same. Okay, so here's a few calorimetry examples. Now we're going to switch gears here and look at some Mathematica examples just to make sure you understand how to do this. Okay, so we have this first one. We have an unknown metal, and we start with the metal at 100 degrees. We place it in some water, and the water is at 24 degrees, and the final temperature of the water is 32.5. So we want to use this data to calculate the specific heat of the metal. All right, so first thing I'm going to do is just list out what we know. We know the mass of the metal is 23.8. We also know that the initial temperature of the metal, Ti of the metal, is equal to 100. And I'm just going to use a lowercase c here. We know the mass of the water is 50 grams. Please pay attention to sig figs here. We know that the initial temperature of the water is 24 degrees Celsius, so 24C. We know the final temperature. Now, the final temperature, remember, is for both the water and the metal because they come to thermal equilibrium. So that's 32.5 degrees Celsius. And the heat capacity of the metal, we don't know, but we do know the heat capacity of water, 4.18, and the units are joules over gram degrees Celsius. Gram C. That's all we need to know. Now we're just going to write it out, plug it in, and solve. So our equation here is the m times c times delta t. So mass of the metal times the specific heat of the metal, which we don't know, times delta T of the metal, which is the final temperature minus the initial temperature. So we know the final temperature is TF. We know the initial temperature is Ti metal. And double equals. Now we know mass of the water times C of the water, which I've just called C for some reason. Oh, you can't do that because I use C as a unit, so we can't do that. So let's call that C of the water. Times TF, which is the final temperature, minus the initial temperature of the water. Now, it's very important to remember that you keep all the information about the water on the left side of the equation, on the right side, and the metal on the left. So the water is on one side, the metal's on the other, just to double check. And we're going to solve for the specific heat of the metal. Only one thing left to do. Remember, we have to make one side negative. Well, let's think about this for a minute. The metal is starting hot and getting colder. So heat is actually lost from the metal. So I'm going to call that side negative just to be accurate or correct. But the truth is, it doesn't matter which side you make negative. They have to be opposite. Okay. But if we want to be totally 100% accurate, we'd make the metal side negative, the water side positive. Shift return, and voila. The specific heat of the metal is 1.11 joules per gram degree Celsius. Woohoo! It all worked. Now, did you know that specific heat is an intensive property? You remember what that is? Intensive property can be used to identify a substance. So if we had a few more clues about this metal and we knew the specific heat of the metal, we could probably use this to help us identify what it is, because it's a characteristic property of any. It's a property that stays the same regardless of the size of the sample. All right, well, there's another problem down here. Let's just take a quick look at this one and see. 10 grams of aluminum, we know the specific heat, we know the temperature, we put it in some water, we want to know the final temperature. Well, we've already done this, so I'm going to leave this one for you to answer. Now I'm going to go back to my PowerPoint. Now, here's what we're going to do in class. Here's our first calorimetry challenge. We're going to use this concept of heat exchange from the system to the surroundings to determine the number of calories in a piece of snack food. In this case, it's a peanut. So what we're going to do here is we're going to actually put water in a soda can. The soda can is actually emptied out, and then rinsed out, and then you put a measured quantity of water in there, say 50 milliliters. We're going to measure that very accurately, and then we're going to put the peanut under there, or potato chip, or whatever snack food we choose, and we're going to burn it. Because you know what happens when you eat food? It's actually metabolized in your body as the equivalent of burning that and releasing the energy. So we're going to release the energy by burning it, and we're going to figure out how many calories are in a peanut. Okay, so in order to know this, we're going to need to collect some data. Obviously, we need the mass of the water in the can, so we've got to measure that pretty accurately. We need the temperature change of the water, so we need the initial temperature of the water and the final temperature of the water after the peanut has finished burning. And we need to know the mass of the peanut. But most importantly, we need to know the amount of peanut that actually burned. When we do this in lab, you'll see that sometimes not every bit of the peanut burns. So you want to take a measure of the piece that you're going to burn before you do anything to it. And then if there's anything left over, you want to measure it again. And then you can use our delta H equation to figure out how much energy was released from that peanut. And then you can figure out the number of calories in the object, in the piece of food. So that will be our first calorimetry experiment in class. We will see you then.